Okay, so today we're going to talk about linear algebra. It doesn't show very well on these. Got those ones a little off, but this is good. So just as a reminder from way back in physics and 311, right? Review of vectors. So a vector is defined by what?
By suffering.
By a magnitude and a direction, right? So we have some sort of magnitude defined as the length of the vector, and then the direction, of course, x, y, or z, or whatever we're working on. Okay. So, and our magnitude is a scalar, and then, of course, the arrow indicates our direction. So ways that we can depict vectors or annotate them, and Cartesian coordinates is mostly what we use in physics or in statics, but we're going to start using more of the matrix form, so we'll have the brackets around it, and you can have it in vertical or horizontal orientation. Either way is the same, and you can see our annotation for our A and B vectors. So when we do vector addition, right, what are we doing for vector addition? If I want to add B plus W, what am I going to do? So anybody remember? It's going to be 1, 2 plus 3, 4, right? This is going to be
7 x's and half the y's, right?
Pardon?
7 x's and half the y's. Like 1 plus 3.
Oh, yes.
Okay.
Sorry, I wasn't following what you were saying. So then we got what, 2 plus 4, right? So this will end up being 4, 6. Right? So if we have 1, 2, so we have one vector there, and 3, 4, something like that maybe. So now if we go 4, 6, we're going to end up somewhere in the middle there, right? Everybody remember that? Makes sense? Oops. Bracket. Okay, so that's our vector addition. And if we want to do a scalar, right? So if my scalar is 2, what's my new vector going to be? 2 times 1 and 2 times 2. So that's my new vector with multiplying it by a scalar. So all we're doing is moving up and down that line, right? Okay, so vector scalar multiplication, dot product. Everybody remember how to do that?
I calculated. Yep.
You can calculate it. Well, we got a pretty simple vector, right? Or pretty simple vectors, right? So if I want to G dot W, it's going to be what? 1, 2 dot 4. So what's my operation? It'll be 1. Well, let's do this so that you don't get confused between the this is going to be 2, 4, right? So this will be 3 plus 8, so it's going to equal 11. Whenever we take the dot product, we end up with a scalar, right? You guys remember doing that? Physics and statics. So those vector operations we're going to apply when we start getting into matrix and linear operations. So if we look at linear equations, or the structure of a linear equation, right? We have a times x plus a2 times x2, as many values as we need. And we're just saying here that a is an element of the real numbers, right? So any real number, 1, 2, 3, 4, 5, minus 1, minus 2.
Shouldn't it go to a and xn?
You're right, it should go to a and xn. Typo on my part. Thank you. So yes, didn't mean to confuse you. So if we have an equation, x minus y equals 1, and 2x plus y equals 6, right? Those would represent two linear equations. Let's see. I don't have a lot of room. So how might we solve those, or go about determining what these two unknowns are, the x and the y?
Solve one for x and y and substitute it to the
Right. So maybe solve the first one for x, substitute it into the other, get y, and then back substitute. Right. So pretty straightforward. I'll just write it out real fast. Equals y plus 1. So we're going to say 2y plus 1 plus y equals 6. This is gonna, no, I don't want to do that. Gonna encroach. Well, I can just erase it. Okay. So that equals 6. So that's going to become what? What's that?
3y plus 2.
Yeah. Equals 6. Well,
2y
what
plus
did I
2
write?
plus y.
Oh, I wrote it out down here. So 2y plus 2 plus y equals 6. So yeah, 3y equals 4. So y is going to equal 4/3, right? So then we can plug that back into x. Equals 4/3 plus 1. So x is going to equal 7/3. Okay. So one way to do it. But if we had lots and lots of equations, 6 or 8 or 10 or 100 or 1,000 of them, this would get pretty tedious and fairly hard to do. Right? So we'll start working on some different and better ways. X minus y equals 1. X plus y equals 6 here. Excellent. So we have some row operations that we can work with. that'll help us deal with our linear equations or our system of linear equations. So a couple of the rules, or 3 of them, that we can work with. We can switch any 2 rows, multiply a row by a constant, or we can add a multiple of one row to another and get a solution. So what does that look like? So if we do, so if this is our beginning equation, we say I, and I'm going to switch 2 rows. That's all we're doing, switching 2 rows. Okay, if we say that we want to multiply one row by a constant, so if we go back to our original order and we say 3 times plus y equals 6, that'll become 3x minus 3y equals 3, 2x plus y equals 6. So there's our equivalent rows. And the third rule, over here. For example of the third rule is where we got x minus y equals 1, 2x plus y equals 6. So if I multiply this by minus 2, right? We're going to end up with minus 2x or plus 2y minus 2, 2x plus y equals 6. Now we say add the multiple of one row to another. So we're multiplying by 2. We can now add these rows together. This is going to go to 0. This will be 3y, and that will be 4. Does that make sense? See how that works? So we can solve for y equals 4 thirds, right? And that was an earlier solution that we had when we were doing substitution. Okay. So if we take this a step further, we can make it even a little easier. So if we stay with that same equation and we put it in matrix form, this should be it. And this is what we will call an augmented matrix. So I'll rewrite it here. 1 minus 1, 1. This is 2, 1, 6. So now we can use our row operations to be able to solve this for the unknowns x and y. Okay, and we say that this portion, 1, this is the coefficient matrix, and this is the constant matrix. Okay, but we can apply now when we're doing these operations. We're going to, try to make. We want leading ones, and we're trying to make zeros underneath them. Okay, so we want to make this become a 0. So the way to do that is multiply this row by minus 2 and add it to this row to make it go away. So it's going to look like this. Let's move over here. So you guys got this. So minus 2 times 1 is minus 2. Minus 2 times a minus 1 is plus 2. And minus 2 times 1 is minus 2 again. And then we have 2, 1, and 6. Right? So this is 0, 3, and 4. So this row didn't change. This is a 0, 3, and a 4. Questions about that? Does that make sense? Okay. So now we want this to become a 1. So we're going to use rule number 2 and multiply that row by 1/3. Right, so 1/3 times 0 is 0. 1/3 times 3 is 1. 1/3 times 4 becomes 4/3. Oops. Okay. So we still need to figure out what our, so we know that, so this is the y term, so we know y is equal to 4/3. We've already done that. But in order to get this to go, we need to multiply this row by 1 and add it to this row, right? So I have 1 times 0, 1 times 1, 1 times 4/3. And we're going to add it to this row. So 1 plus 0, oops, not 0, 1. Minus 1 plus 1 is 0. 1 plus 4/3 becomes 7/3. So we'll squish this in down here. So we have 1, 0, 7/3. 0, 1, 4/3. So that's the solution to those two linear equations. Questions? Make sense? You can follow that anyway. And let's see, did I plug it back in? Sure. So if we say what? 7/3 minus 4/3 equals 1, and 2 times 7/3 plus 4/3 equals 6. All right, or at least it better. So this is going to become what? 3/3, so that's 1. 14 thirds plus 4, 14, 18 thirds, so 3 and 18 is 6. Worked. Okay, so that's how we can use those row operations to solve for, and matrices to solve for the unknowns. So that was an example of two lines that intersected, or equations of two lines that intersected. So what else maybe can happen? Oops. So what if we do this one? So what's this going to be? 1, 1, 4, 3, 3, and 6. Okay, so what should my first operation be? I want to make this go to 0. So if we do -3, add it to that. So -3 plus 3 is going to be, well, let's see, this row isn't changing, so we'll go ahead and put that one in. So 3 plus 3 is going to be 0. -3 plus 3 is going to be 0. -12 plus 6 is -6, right? Well, 0 doesn't equal -6, right? So this is a undefined, or we would say 0 doesn't equal -6. So this would be an example of parallel lines. There's no solution, right? So what about this one? So let's see, we got 4 -2, 16, -8, oops, 1 and 4. So what do we want to do first? So we want to make this a 1. So if we divide through by 1/4 for that first row, that's going to be a 1 minus 2/4 is going to be 1/2. Then this will be 1/4, right? 16 minus 8 and 4. Okay, so now we're trying to make this go to 0, right? So it's going to be -16. So 1 minus 1/2. 1/4. Because that row's not changing. So -16 plus 16 is 0. Minus and minus plus 8 minus 8 is 0. Minus, this is 4 plus 4, so that goes to 0. Okay. So this is an example of one line, single line. And we have infinite solutions. Because what we have to do is we're going to parameterize this equation. So we have x minus 1/2 y equals 1/4. Right? So x, well, what we're going to say is we're going to say let y equal t. So if we say x and y, so y equals t, and x is going to equal, if we take this to the other side, it's going to be 1/2. We said y was t plus 1/4. Whoops. So now, any value, any real number that we put in for t, we're going to get a solution for this equation. Okay, and it's all going to be along one line, whatever direction that's going. So these will come into play when we get a little farther here into matrices. So, so we started doing it, but what we're essentially doing is called Gaussian elimination. And what we're trying to do is get this so that we have leading ones and zeros under all the ones. So this one's a little more complicated. But this is our series of equations, and we're just going to make it into a matrix, right? So we have what? 1, 1, 2. Our augmented matrix, that'll be an 8. This is -1, -1, 3, 1, 3, -7, 4, and 10. Right? So when you're doing Gaussian elimination, sometimes this will get referred to as the pivot, right? And then when we get to this one, it becomes the pivot, and so on. It doesn't matter how many rows you have. And we're trying to eliminate these and make them 0, right? So in order to do that, we're going to multiply by 1, and we're going to multiply by -3 to make those go to 0, right? So what do we got? So this stays the same, 1, 2, 8. So 1 times 1 plus a -1, or -1 is going to be 0. 1 and 1, -1, 0. 2 plus 3 is going to be 5. 8 plus 1 is going to be 9. And when we're doing this, we have to work until all of these are zeros, however many equations we have. Otherwise, this process won't work. So -3 plus a 3 is 0. -3 -7 is 10. -6 plus 4 is -2. What's -3? 20 -24 plus 10. So 14. Negative. Thank you. Yeah, it's real easy to mess up the sign or screw up the math, and then your matrix doesn't work, and you have to go back and figure out where you messed up. It's a real pain in the butt. Okay, so next, let's see. Did I do this right? 1. Okay. So we need a 1 here. Let's make sure I'm tracking. Oh, this is a different. Well, we'll keep going. Okay, so I need to get a 1 in this position, so I gotta switch these rows, right? So 0, -10, -2, -14, 5, and 9. So I want to make that a 1, so this is going to be a -1/10, right? So 1, 1, 2, 8. So this is a 0, this becomes a 1, this is going to become a 5, right? 2 over 10, oh no, it'll be 1/5 positive, and this will be 14 over 10, 0, 0, 5, and 9. Okay, so now we need to make this a 1, so 1/5. So 14 tenths. This will be 1/5. now we're at a point that this is called row echelon form, right? So we know that x3 equals 9/5, so we can plug it in to this equation and solve and back calculate and determine what the solution is for the others. I have an easier example to go through for row reduction. Yeah. So I've got an easier one to go through. But anyway, so you can solve through, and we'll do another example. But you're getting the idea, right? And so what we're looking at when we're dealing with these matrices is we have our number of rows and our number of columns. Or well, this is rows, that's columns. Okay. So that if we take our equation a little bit farther, so if I have x1 plus x2 2x3 equals 8 minus x1 minus 2x2 plus 3x3 1 3x minus 7 x plus 4 x3 equals 10. Okay, so if we want to get to reduce this, we're going to do 1 minus 3 again. So what does that become? 1, 1, 2, 8. So this will be 0, minus 1, 5, 9, 0, minus 10, plus 2, 14. So if we do minus 1 here, minus 5, minus 9. So let's see, we want to get rid of this 10. This is going to be a 10 here. So now we're going to have, let's see, which that's 3. 8. 9. This will be 0. So it's 2. Now I want to get rid of this. So 152. I need it to be minus. This becomes 2. So here's our reduced row echelon form, but if we take and multiply 5 into that row and a minus 2 into that row, and what do we get? 1, 1, 0, 4, 2, that doesn't change. Alright, so we're almost there. Gotta get rid of that guy. So let's put it over here. So this is our reduced row echelon form. Oops. Right. So our x1 is equal to 3, x2 is equal to 1, and x3 is equal to 2. Plug those back into that, and those systems of equations will work out. So this is the basis for the beginnings of what we're doing, or what's going on in the background when we're dealing with our finite element analysis. There's a couple more operations we got to do, or learn how to do, or at least know about. So if we want to do matrix addition, the only requirement we have is that, you know, these both matrices that are being added together have to be the same size. So this is 2 rows by 2 columns, and you can add it to a 2 by 2. But if you have a 2 by 3, then you know you can't add them together. Have to be the same size. And so again, we're doing like our vector addition: 2 plus 2 minus 3 plus 1 minus 3, 0, 5, and 4. Okay, and then just the general form depicted there. Okay, we can also do scalars with matrices. So 10 times 10, 10 times 4.5, 10 times minus 4.5, 10 times minus 6, and we get whatever's going on there. Okay, now when it gets to multiplication, it's a little bit trickier. Okay, and the important thing is that when you're looking at your m by n and your n by p, these two have to match. So this 3 and this 3 have to be equal in order for you to do matrix multiplication. Okay, so this one is a 2 by 2 times a 2 by 2. So these two are equal, so that's okay. And we're going to end up with a 2 by 2 matrix because you're looking at those two values. So how do we go about doing this? Tricky. So essentially what we're going to do is we're going to take this row and multiply it by that column. And then we can take this row and multiply it by that column, or this column, excuse me. Okay? And we'll do both columns actually. So we're going to, I'll write it out. 2, 3, 4. Okay, so we're going to do this row, this column. And we're doing 1 times 0 plus 2 times 5. So what does that look like? Dot product, right? So what do we end up with? 2 times 5, so this is 10, right? So now, so we did this row, that column, Now we'll do this row and the first column again. So 3 times 0 plus 4 times 5. So that's what, 20? 1, 2, 3, 4. So now we can do, let's go back to this row and this column. So this will be 1 times 1 plus 2 times 3. So 6, so what's that, 7? So let's see, this row and this column. So 3 times 1 plus 4 times 3. So 3, 12, 15, right? 3. Yeah. And this is kind of in the way. Let's see, I have a blank. You guys still see that?
Yep.
So this is 10, 20, 7, 15. Does that make sense how those go? So if we write 1, 2, 3, 4, 5, 4, 5, 3 equals 10, 20, 7, 15. Okay, so that's how do the matrix math or matrix multiplication. So I think I have one more example. Okay, so can we do the matrix multiplication for this particular setup? So let's see, what do we got here? We've got a 3 by 2 matrix, right? And this is a 2 by 2 matrix. So these two are equal, so we're okay. So what size matrix are we going to end up with? 3 by 2. So this will be a 3 by 2 matrix. Okay? So we have 3, 0, minus 1, 2, 1, 1. 4, minus 1, 0, 2. Okay, so has to equal, we're going to have a 3 by 2. So we're going to do this row times that column goes here, right? This row times that column goes in this position. This row times that column is going to go here. This row, that column, right? So what do we got? 3 times 4 plus 0 times 0. So this is going to be 12. Minus 1 times 4 is minus 4. Plus 2 times 0 is 2. Or it's going to be 0, so it's minus 4, right? 1 times 4 plus 1 times 0 is 0, so this is 4. 3 times the minus 1, minus 3 plus 0, so minus 3. Minus 1 is a 1, plus 4 is 5. Minus 1 plus 2 is going to be 1, right? That make sense? Questions? Easy peasy. Oh. Okay. So, how does this all relate to what we're doing? So, a lot of what we're going to be dealing with is going to be in this form, AX equals B. So, our A matrix, our X, and equal to B, right? An example of that would be Kirchhoffs Law, right? So, this is our A, our X, and our B. So we have our stress in 3 axis, we have our E in 3 axis. For say steel, that should be isotropic and homogeneous, right? And then whatever strain is happening in those various directions. Okay, and then you're going to do the matrix multiplication to determine what your stresses are. A couple other things to note is matrix multiplication is not commutative, right? So A times B is not equal to B times A. However, the multiplication is associative, so you can do A times BC is the same as AB times C, and the distributive law also holds through, or holds true, so that can be followed through. Let's see. So I'm going to skip the next 2. Okay, so application. How do we put this all to work? Right? Kirchhoffs Law. Anybody remember Kirchhoffs from basic electricity? We hope, right? Basically saying 2 things: conservation of current and conservation of voltage. So conservation of current, any point or node, right, of a circuit, the sum of the inflowing current equals the sum of the outflowing current. And then conservation of voltage is any closed loop. So we have a loop here, we have a loop here. The sum of all the voltage drops, the resistors, equals the impressed electromotive force. So the battery or wherever the energy is coming from. So how are we going to use our matrix algebra to solve for the current at I1, I2, and I3? How might we go about doing that? Anybody got any ideas? Well, we're going to create a series of, or a system of equations, put it in a matrix, and do Gaussian elimination to determine what the solution is. Right? Easy peasy. So to set this up, we're going to start with the nodes and apply Kirchhoffs conservation of current. Right? So if we start with node Q there. And if we're looking at current, so what's happening at node Q with the current? What's I1 doing? It's leaving. So we'll say minus I1. Let's see, I2 is going in, so we'll call that plus. And I3 is also leaving, minus I3. And that has to what? Sum to 0, right? Whatever's going out, it's got to come in, right? That's definition of conservation. So let's do node P. So what do we got? I1 is plus minus I2 plus I3, again, equal to 0. Okay, so now if we look at voltages, we're going to say the left loop, right? So what do we got? We said the voltages was the sum of the resistance and the electromotive force. So we've got what, 20, and voltage, right? Volts equals IR. So 20I. Let's see, we're going around. So we've got a 10. So for I1, we only have 20. For I2, we've got 10. We got a 0 here, equals 80 volts. So the right loop, what's the right loop going to look like? Do I have anything for I1?
No.
No, so it's going to be 0. What's I2? Well, I2 is here to here, so it's 10. And then I3 will be what, 25 equals 90. So that looks like a system of equations, right? So we can make a matrix out of that, right? So we got minus 1, 1, minus 1, 0, 1, minus 1, 0, 20, 10, 0, 80, 0, 10, 25, 90. And now we do Gaussian elimination, right? And away we go. Now, one thing we can comment about this is we have, what, 3 unknowns, right? But we have 4 equations. So we're what we call overdetermined. But that's okay. So we want this to be a 1, right? So we can multiply through by minus 1, swap all the signs, or we can switch 2 rows, doesn't matter. Right? Let's see. Here's my solution. Here's my solution. You want me to go through all the steps, or you just want the solution? You guys get the steps? Is that making sense? Okay. So eventually, one of these, well, here, let's do an intermediate step of interest here. Let's see, where to go? Well, if I swap these 2 rows, 1 minus 1, 1, 0, 1 minus 1, 2, 10. PB, 0, 10, 25, PB. So if I do 0, 1, 20, so I end up with 0. This goes to all zeros. So this whole row went to 0. That's fine. I can just swap those two rows, put it to the. Anytime you have rows of zeros, push it to the bottom. Okay. So then our final solution is going to be 1, 0, 0, 2, 0, 1, 0, 4, 0, 0, 1, 2, 0. So what? I1 equals 2 amps. I2 equals 4 amps. And I3 equals 2 amps. So that's how we can apply a system of linear equations and do reduced row echelon form of Gaussian elimination to get the solution for our unknowns. Okay, so let's look at another example. So this time it's going to be intersections. But again, we can apply, Kirchhoffs principle, right? At the nodes, whatever goes in's got to come out. So how might we set up our, so what's our process going to be? How are we going to solve this? What's the plan? So we're going to set up a series of linear equations that represent the nodes of each of the intersections. Put it in matrix form and Gaussian elimination to get to reduced row echelon form to produce our unknown. Or produce a solution for our unknowns. So let's go ahead and set this up. And how do I label these? Let's see, 64. So this is A. This is going to be B. So this will be C, and this will be D. Okay. So at A, what might my equation look like for node A? What's going in? So these arrows going in that direction. This one's going in. So we have what? Plus 600 plus 400 minus x1 minus x4. Right? It's going to be equal to 0. Okay, at B, what do we got? Minus 800 minus 800 plus x1 plus x2, right? At C, plus 1200 plus 1000 minus x2 x2 minus x3, 0. Finally at D, minus 1,000, minus 600, plus x3 plus x4. Okay. Well, we want to get this looking more like a linear equation, right? So we're going to say x1, x4, or minus x4 equals 1,000, right? Or minus 1,000. And so then this is going to be x1 plus x2 equals what, 1,600? Minus x2 minus x3 is what, minus 1,400, is that right? No, 2,200. Now I got x3, x4 plus 16, right? Did I get that right? So my augmented matrix is going to be 1, 0, 0, minus 1, minus 1,000.
No, the next one should be negative.
Pardon?
X1, the first one should be negative.
Oh, yep. Thank you. So then this is a 1, a 1, a 0, 0, 16, 0, minus 1, 0, minus 2,200, 0, 0, 1, 1, 1,600. So there's our matrix. Now we can row reduce it. And what do we end up with? Well, we're going to end up, let's see, where do I have it in here, right? I have the, well, we'll squish it in here. Okay, so we get all done. We're going to have 1, 0, 0, 1. This is 1,000. Have 0, 1, 0, minus 1, 600. 0, 0, 1, 1, 1,600. 0, 0, 0, 0, 0. So we have this row of zeros at the bottom, and we have one row that's got two unknowns in it. So what do we have to do? We have to parameterize. So that means that this, right, we're going to set x4 equal to t, solve for the others. So that means that this solution has infinite solutions. So any number I put in for t is going to produce a solution for all the rest of them, right? So if we leave that, I'll redo the rest of it over here, right? So x1 equal what? Minus t minus 1,000. x2 equals t plus 600. x3 minus t plus 1,600. x4 equals t. So I can put any whole number in for t, and I'll get a solution for all the rest of those equations, right? So if I say t equals 100, right? So x1 is going to be what? Minus 100 minus 1,000 So that's going to be minus 1100, right? Or, no, this is supposed to be plus. So that's 900. X2 is 100 plus 600, 700. X3 is minus 100 plus 1600 is 1500. X4 equals 100. So if I have 100 cars go through X4, those are the numbers that are going to go through the other values. Okay. So that's how we use the linear algebra to apply these types of situations. And as we get into Wednesday and forces and displacements, we'll take advantage of those matrix and linear equations to develop our displacement.